Hello. So today we're going to talk about two applications of k-means clustering. Specifically, we'll talk about k-means clustering as a data pre-processing tool, and we'll also talk about k-means clustering in image segmentation. However, to keep this lecture focused and relatively short, here I'll only talk about the data pre-processing part, and I'll make a second part of a video lecture where I'll talk about image processing. Okay, so we have seen in the past a few ways of trying to improve the performance of a base learner. For example, we talked about bagging random forests and boosting techniques and voting classifiers. Those were all ways of trying to sort of improve upon a low-level learner, okay? It turns out that another way to try to improve a little bit on the performance of some predictor or model is to first kind of transform your data, okay? We've already seen this before, right? So when we fit, for example, logistic regression in the past, the first thing we typically did was scale our data. So this is one transformation that we saw oftentimes results in an improved performance of the model. Okay, so it turns out that another transformation that oftentimes results in an improved model is by clustering your data first. Okay, so basically you apply a k-means clustering algorithm to your data first, and only after you do that you fit a model like a predictor such as logistic regression. So in this lecture, we will specifically focus on trying to improve logistic regression. So first thing we're going to do is we're going to create a baseline using the airline satisfaction data set. So what we're going to do is we're going to fit and tune the logistic regression and get as much performance as we can out of it. And then we're going to transform our data first by creating this pipeline that we'll talk about in just a little bit. And so basically we're going to scale our data first, apply k-means clustering, and only on top of that build a logistic regression. Okay, so that's the sense in which we're going to use k-means clustering as a pre-processing or data pre-processing tool. Okay, awesome. So let's get it going. In the first few lines of codes here, what I'm going to do is I'll just import some of these standard libraries that we always do. And here I'm going to import the airline data set just as we've done in the past. So this is exactly what we've done in the past. And because this data set has over 100,000 subjects, for computational purposes, I'm only going to select randomly 15,000 of those samples, basically. Here again, we're just converting the qualitative variables into dummy numerical variables. And as I've said in the past, it's always a good practice to set aside a validation set if you can afford it, so that once you have tuned your model, you can actually check the performance of your best model on this validation set that your model has not seen during any of the tuning stages. And because I'm going to fit logistic regression first to create a baseline of performance, and so by a baseline I just mean, whatever I do next, I have something to compare it to. I'm going to scale the data here again. So this is one transformation that I'm performing to the data. And as we'll see in just a little bit, when I built this pipeline, it's actually not necessary, and it's not actually recommended either to scale the data first, but rather scale it as part of the pipeline. So I'll talk about that in just a little bit and why that's the case. So in any case, so here is the scaled data. Okay, so we have 23 columns. And here is the scaled validation set. All right, so in this next block of code, all I'm doing here is I'm fitting a logistic regression. This is identical to what we've done, I think, 2 or 3 lectures ago when we talked about ensemble models and adaptive boosting with logistic regression as a base learner. Okay, and so technically here I'm performing a grid search. I'm manually performing a grid search, but in a little bit we're also going to use the built-in grid search method to do the same, basically look for the best parameters. And once we do that, so here is a plot that's plotting the accuracy score versus the parameter C. So remember, this parameter C is what controls the strength of these regularizations in logistic regression. And as we can see, it seems like maybe a logistic regression with a L2 penalty and a parameter C of 0.51 is giving us the best results. So here what I will do is I'll train again logistic regression using the train set with these parameters, and then I'll use that trained model to predict or to make predictions on the validation set. So remember, the validation set was never entered the picture here, so the model has never seen it during any of these tuning stages. Okay, so it's there's basically no information that's leaking from there here. Okay, and this is what we got before as well. So the baseline for us is that even logistic regression, one of the simplest models on its own, is achieving an accuracy score of a little over 87%. So for what we're going to do next is we're going to try to improve on this score, but we're going to try to improve on this score by first performing an extra transformation on our data. So rather than fitting multiple models as we've done in the past with these ensemble models, here we're performing another transformation to the data in the hopes that it will improve the result. And I just want to say it or emphasize it here that this should only be an extra tool that you have in your toolbox. It may not always work. So, but it is something that you can try when you're trying to improve upon a model, okay? And Python has a really neat pipeline method built in. And pipeline is basically what it sounds. It is a method where you sequentially apply a list of transforms where the final estimator or the final model has to be a predictor, okay? So it's important to keep in mind that all the intermediate steps basically in a pipeline must be some kind of transformation of your data. So it does not, you cannot build, I guess, a prediction model at stage 2 and at stage 3 on top of it build another prediction model. That's called stacking, and we might talk about that in the past, but as far as pipeline goes, again, all the intermediate models need to be transformation, some kind of transformation of your data. All right, so let me just talk about, so I'm not going to run this code here because it actually takes a while for this to run. It may take several minutes, but let me just walk through it. So what I'm doing, and I'll explain how to build a pipeline as well. So we're going to use, one of the advantages of the pipeline is that once you stack sort of these transformations and then at the end your predictor, you can tune the whole pipeline at the same time using cross-validation and grid search. Okay, so you don't need to tune one model first and then another one on top of it. That's actually not even recommended because since the models are communicating with one another, you need that to use that information that leaks between the models, basically. Okay. So the plan here is again to use as a predictor logistic regression. Okay. And we're going to perform sort of a manual grid search, just as we've done in the past, and then I'm going to show you how to actually use the built-in grid search method to do the same. And here's what we're going to do. We're going to loop through a bunch of clusters. In other words, we're going to first, so let me move, I guess, here in the pipeline, how you create a pipeline. So to create a pipeline, you simply import it from sklearn.pipeline, and then you import this pipeline with a capital P. And then in the pipeline here, you need to provide a sequence of models that you want to perform one after the other. Okay? What does that mean? It means here that I first want to scale my data. That's why I have written here as a tuple, where the first guy here is the name of the model, like what you can call it whatever you want, and then here is the actual model that you want to perform, or the transformation that you want to perform to your data. After you have scaled your data, what the pipeline here model will do is it will perform this other transformation. In other words, it will cluster your data into K clusters. Okay? And now it's important here to notice that these new clusters, okay, for example, if you create 5 clusters, these will be the new features or the new columns that you feed into the next or into the predictor. So although here our airline data set, let me go back up, has 23 columns, when, for example, K is 12, what's going to happen is at this stage you're going to basically feed 12 features or a data frame with 12 columns into your predictor. Okay, and that's what we're going to do. We're going to, because we want to figure out the optimal number of clusters as well, we're going to loop through a couple of those, and ideally you'd want to loop through a lot more than what I have here, but in the interest of time, because it was taking too long, I'm only going from 12 to 19, and I'm moving by a step of 2. And then again, I'm going to check different regularizations, L1 and L2, and then also I'm going to look for different strengths of these regularizations. Okay, and as always, we use cross-validation. So here, after you create your pipeline, then you use cross-validation where you treat this guy as you'd treat any other model that we in the past. Okay, in other words, you use cross-validate and then you just write pipeline there, X train, Y train. And here's what I meant when I said that we're not going to scale the data or use the scaled data a priori in the pipeline here. And that's actually important if you want to be really picky and you want to, you really want okay, so here's why. Here's why this is important. So first off, let me just show you that this X train and Y train is actually the unscaled data. Now why, if you really want to be careful, then the reason why you don't want to actually scale the data a priori is because when you scale the entire data set before splitting it into training and the test set, actually there is information leaking into the test set. Okay, and that's why when you use the test set to compute the accuracy score, you may overestimate the accuracy score. So basically, since we want the training set and the test set to be as independent as possible, you don't want to scale your data a priori, but rather when you perform here cross-validation with 5 splits, first this training data will be split into 5 subsets, and then 4 of those that will be used for training will be scaled separately, and then the other one that will be used for testing will be scaled separately. And that's why there is no communication or there's no information leaking from one into the other. Okay. Anyway, so once you run this, then here again, just as I've done before, all I'm doing is I'm plotting box plots where I essentially am plotting the accuracy versus the number of estimators, right? Actually, this is not the number of estimators. This is the parameter C. Okay, anyway, sorry about that. Okay, I guess I forgot to look at that. Anyway, so yeah, so I'm plotting accuracy looking at different clusters, and the x-axis here, since I'm using logistic regression, and one of the parameters that I considered in logistic regression was C. And I think to make this simple, I actually didn't look at L1 at all, but I only looked at L2. But you can look at L1 as well if you want to. All right, so looking at this, it seems like if we first split our data, or if we first transform our data into 18 clusters and then apply logistic regression with a penalty of L2 and a C of 1.3 or 0.3, we might beat our performance before. So for here, let me use it 0.3. One thing that I want to keep in mind though is because cluster 18 turns out to be the one that's the best, maybe, you know, if we looked further, or if we first transformed our data into more clusters before applying logistic regression, then we may have done better, and that's actually what we do next. But anyway, so here we fit, again, we create a pipeline where after scaling our data, we transform our data into 18 clusters. Okay, we create 18 clusters, and then on top of it we fit the logistic regression with these parameters. And once you actually compute the accuracy score on the validation set, you get 0.88. This is already an improvement upon 0.87 by over 1%. However, as I pointed out here, since transforming our data into 18 clusters, and that was the largest I could look for, or that was as far as I could go in my parameter space here, then maybe we should have looked further. And that's exactly what I'm going to do next, but I'm going to use this neat grid search built-in method to do that. And the way grid search works is basically very similar to what we manually did. However, so what you do first is you declare the parameters of any of these transformations in your pipeline, okay, that you want to tune. So specifically, since I want to look at different clusters and I want to look at different values of C, those are the two parameters I declare here. So it needs to be a dictionary, and it has to start with the name of your model. So this is why, you know, this name here is important now. So this one and this one here need to match exactly, and then a double underscore, basically underscore, and then next you write the name of the parameter you want to tune. So here I want the n clusters, and that's why I give a range of values to loop over. And you do the same thing for LG, okay? If I had called this logreg, for example, then I would need to write here logreg exactly, and then here underscore underscore twice, and then the parameter you want to tune. And here, basically, I mean, since I'm looking from 26 to 38, I'm only trying to cluster our data into anywhere between 26 and 38 clusters. So if this was a real, live project, then you'd do the same and you'd start way lower, for example, at 12, and go maybe even more to like 50. But it will take several minutes, that's why I'm not doing it here. And once you run this, so now you do the same thing here, and once you run this, you can extract the best parameters and the best estimators and the best score out of this model. And to extract the best score, you just do whatever you called it here. So here I called this model CLF underscore grid. And so if you do CLF underscore grid dot best score, then we get this guy. So in other words, we managed actually to get a 0.893 score. But this is a score that we got out of the cross-validation, right? And then if I want to know, well, which parameters of our model gave or resulted in this best score, then you can find that out by just doing it again, CLF underscore grid underscore, dot best params. And here we find out that so after scaling your data, if you cluster it into 32 clusters and use a C of 1.9, that seems to give you the best score. And now you can also extract the best parameter, the best estimator from CLF underline grid. So here, best estimator is exactly this. It's the pipeline, this pipeline model here, with scalar as a first transformation, then k-means clustering with 32 clusters as a second transformation, and then with a predictor of logistic regression with a penalty of L2 and C of 1.9. And if you use that to compute the accuracy score in your the accuracy score of using the validation set, so this is a validation accuracy score, you get a 0.898. This is a significant improvement over what we got with just using logistic regression alone. So here we got a 0.87, here we got almost 90% accuracy, okay? This may not seem a lot, but as I've mentioned it in the past, oftentimes it's hard to increase. It's easy to achieve first, like, 80-90% to begin with, but then if you want to improve further, it takes sometimes quite a bit of work and more data pre-processing like this. So in this case, basically, by using k-means clustering as a transformation before applying logistic regression, we managed to reduce the error rate by a little over 21% actually. In other words, our error rate when just using logistic regression alone was about 12.77%, and when we used k-means clustering to transform our data first, it dropped to about 10%. And I want to again re-emphasize that this may not always work. For example, in this particular case, although I didn't do a very extensive grid search for parameters, but if you try to improve on the accuracy score that we got using random forest, then this is actually not, you're most likely not going to be able to do that, because again, there's I guess some other reasons in the background, going on in the background, but it's definitely one tool to keep in mind when you're working when you're building prediction models. So this is it for this lecture. So if you have questions, feel free to email me. And so for the second part of the lecture, we're going to talk about k-means clustering in image segmentation.